In this Module 5 self-check, I will go over the answers and then I'll come back and talk about each one in order. Number 1 is C, the 6 Newton force. 2 is negative 18 joules E. 3 is B. 4 is C. 5 is B. 6 is E. 7 is A. 8 is D. 9 is A. 10 is E. And 11 is C. All right, so let's go ahead and talk about each one of these. The force that does the most work is the one that has the largest parallel component. This one here, the work is 0 because the force and the displacement are 0. This one, it would be 8 times d times the cosine of 60. And 8 cosine 60 is 4, which is smaller than the 6 Newton force. So the 6 Newton force does the most work. For number 2, what is the work done by the force of friction in this situation? Well, the friction force, remember, always is going to point opposite the motion of something, so that it's always going to be negative. So work by friction is negative. It takes energy away from the system. The other way to think about that is the angle between the friction and the displacement is 180 degrees, and the cosine of 180 is -1. So then we also need the magnitude of the force, which was 6 newtons, and the displacement, which was 3. So 6 times 3 is 18 joules, and then negative, again, because friction is opposite the displacement. The work done by the normal force is going to be perpendicular to the displacement, so the work would be 0. Again, parallel components are what matters. For number 4, the tractor driving at a constant speed pulls the sled loaded with firewood. So here, the key idea is a constant speed. That means that the change in kinetic energy is 0, so the net work is 0. So when it talks about the total work, that's the net work, and because there's no change in speed, there's no net work done. All right, acceleration, very importantly, is the time rate change of the velocity, not dv dx. So keep it in mind when we do our calculus, what our variable is exceptionally important. And that comes into play in number 6 here. If you tried to just integrate this like you would, basically dividing by the mass, and getting acceleration and then integrating to get velocity, that's not going to work because this is a function of position. So instead, we would have to solve this by saying that it's the work, and it starts from rest at x equals 0. It goes to x equals 2 meters. And so it's then f sub x, so 2x plus 2 dx. We would then execute that integral and then set that equal to 1/2 m v final squared minus 1/2 m v initial squared. And so when you solve that, you do not get any of the answers that are shown. For number 7, you're standing in the elevator and it's moving upwards. That means that your displacement is going to be upwards. Now the force of gravity is downwards. So they're opposite each other. It's not, with Newton's second law, we cared about the direction of the acceleration. Here with work, we care about the direction of the displacement. So the displacement is up, the force is down, so the work is negative. For number 8, we have circular motion. So this is where we have to be very careful about what the dot product means. Work is the integral of f dot dr. Remember the scalar product between the force and the displacement. So if I look at this point in the circle, the tension, right? So it's talking about the tension force. The tension points towards the center of the circle. And what's dr? Dr is a tiny little bit of path length. So dr at any given time would be equal to, and I'll zoom in so we can see a little bit better, dr would be equal to this tiny little path length right here that is parallel to the motion. If I was over here, my dr would be this tiny little path length. Now, why that's important is because if we look, we can see that dr and my tension are perpendicular to each other. And perpendicular for the displacement and the force means that the work is zero. So T dot dr equals 0 for the entire path. So what that means is that the work is equal to 0. And it doesn't matter. It says for 1/2 of a revolution. This could be a quarter revolution, an eighth of a revolution, a whole revolution. It really doesn't matter. It's 0. The work done by tension is 0. So the work by tension is always 0. Okay, and then we're almost done. So to number 9, we have here these 2 blocks on our pulley, and they're moving as shown. And it's asked, okay, what is the total work after they've both moved the same displacement? So they're both going to move the same amount because we have an ideal string. So they're going to move the same position as a function of time. So they're going to have the same velocity as a function of time. So they're going to have the same acceleration as a function of time. So they have the same speed, but one of them's heavier. But so that means the 8 kilogram mass has a larger kinetic energy because it goes as 1/2 mv squared. So the mass means that it has a larger kinetic energy. And so a higher mass, a higher change in kinetic energy, more work done for the larger block. Another way to think about this is that you need more net force to give the 8 kilogram block the same acceleration. So it has more net force over the same distance, more work. All right, number 10, we have the force on a particle here, and this is just a 2-dimensional particle. If you go through, you can see that you would have the limits in the x direction would be equal from 0 to 3, because 3 is the final x position. In y, it would go from 0 to 2, because it's the final y position. And then it's just equal to f sub x dx and f sub y dy. So just using what we know about the general equation for work and the video that talked about how we can use this equation of the integral of the scalar product. And then lastly, number 11, these are constant forces. So F is constant. So the work is just going to be equal to F sub x delta x plus F sub y delta y plus F sub z delta z. Now this is only 2 dimensions, so this one over here, we don't have a z component to worry about. So all we're doing is just going to take 3 for our x component of the force times -2, that's our displacement in x, and then add it to -2, the y component of the force, and then times 3, our displacement in y. So we have -6 plus -6. This is not a vector, it is a scalar product. So -6 plus -6 is -12 joules. All right, let me know if you have any questions.